Alright, let's continue on with the Wittig reaction. Let's look at an example and then work more on this chapter of aldehydes and ketone reactions. So, continuing on with Wittig, here we have this aldehyde, CH3CH2, C double bond OH. Here is our Wittig reagent. Note I've drawn it in the double bond form because that makes it easier to figure out what's the product. If we've got a carbon double bond to the phosphorus here, this carbon has a hydrogen, and it also has 4 CH2s and a CH3. Note, to solve this problem, we literally just get rid of this oxygen, get rid of the triphenylphosphine, double bond this carbon here to that carbon here. And note we get these two products. Note that the two hydrogens, one from the original aldehyde, one from our Wittig reagent, could either be trans to each other or cis to each other. Recall that if the two hydrogens are the two group number 1, priority 1 groups are on opposite sides, that is the E isomer. If the two priority ones are on the same side of the double bond, if we drew a line along this double bond just like this, we see these two groups on the same side of the double bond, that is the Z isomer. And you get 59% E, 41% Z in this case. Any guesses to why we have more of the E isomer? Correct, steric hindrance. All right. So, question. This is what I want to make. I want to take a cyclopentane double bonded to a carbon with a hydrogen and a methyl. How will we do it? Well, looks pretty straightforward. If I see, okay, I've got a double bond here, I know I can make carbon-carbon double bonds with the Wittig reaction. I just need to have a carbon double bond oxygen and a Wittig reagent, triphenylphosphine, carbon with a hydrogen and a CH3. So this side of my molecule comes from the Wittig reagent. This side of my molecule comes from this ketone. And I make this Wittig reagent using just CH3CH2X, just a normal ethyl bromide, and triphenylphosphine. Note, I could have gone the other way. I could have used this aldehyde here and made this Wittig reagent. Either way will work. All right. And what's really nice is when we look at various ways to make it, there can be different ways to make different molecules. We can make double bonds. We've made them before doing elimination reactions. So if I had this ketone, cyclohexanone, and I wanted to make this double bond here to a CH2, one could think, well, I know different ways to do that. First way is Wittig. Just take the cyclohexanone, make the Wittig reagent, do the reaction, and you get that. Or, old school, hey, check it out. Let's do a Grignard reaction. Here's our carbonyl. Attack it with the Grignard reagent, followed by water. We know that will put a methyl on here and change that to the alcohol. Yeah, there it is. A little sulfuric acid means we get dehydration, acid-catalyzed dehydration of the alcohol to make the alkene. Note that here's our alpha carbon, so we have beta hydrogens here because elimination reactions are beta hydrogen elimination. Note we would get this as our major product, this is our minor product, according to Zaitse's rule. Also note that the product we want is the minor product. So which way is better? Doing the Wittig reaction where we only get this one product? Or doing a 1-2 step reaction where the thing we want is the minor product at the end of 2 steps. Yeah, that's right. Wittig would be much better for this. All right, let's continue on. Let's look at the addition of amines to aldehydes and ketones. All right, truthfully, we'll show the mechanism. I'm not crazy jazz that you make you know the mechanism. It's good to know the mechanism here, but I'm not going to ask you about the mechanism of this reaction on exams. But it's good to know what's going on. My main point is if you have an aldehyde or a ketone and you react it with an amine and a mild acid, if it's a primary amine, RNH2, we're going to end up with an immine. the carbon double bond oxygen will be replaced with the carbon double bond nitrogen of the amine. We had one R group on our amine. That one R group stays. These two hydrogens are gone. This oxygen is gone. Yeah, that's water. Two hydrogens and an oxygen is water. So to get this reaction to go, you take your aldehyde or ketone, at a primary amine under mild acid conditions, pH 4 to 5. Note if you have a strong acid, if you put it under strongly acidic conditions, you're just going to protonate this amine and it won't be a nucleophile anymore, and so the reaction will just do nothing. So you need mild acid. But when you do add the mild acid, we'll go over the mechanism in a minute, you form this guy here. One could see how the lone pair on this nitrogen will attack this carbon, have the OH there, and then we get rid of water to make this imine. Carbon double bond nitrogen is an imine. And for the exam purposes, at this point I'm just hoping you realize, okay, I've got a ketone, I've got an amine. What reaction is going to happen? Ketone plus an amine, it's a primary amine, makes the imine. I'm just going to take this carbon double bond oxygen, replace it with carbon double bond nitrogen, and these two hydrogens will be gone to get that product. And that's my imine there. All right. Let's look at the mechanism of this reaction. We'll go through it quickly. A lot of it you probably have figured out on your own or said, oh, okay, well that makes sense. Lone pair on the nitrogen attacks the carbonyl carbon because it's partial positively charged. Pi bond breaks to make the negative charge on here. We can do aqueous workup. What really happens is we get a proton transfer reaction. Note, when this nitrogen, which has a lone pair on it, two hydrogens and one R group on there, when it attacks this carbonyl carbon, now the nitrogen has 4 bonds coming from it. One to carbon, two hydrogens, and one to this R group. That makes that nitrogen positively charged. The nitrogen with a positive charge and hydrogens on it normally would go through a deprotonation reaction, but in this case, this wants to deprotonate, this O- wants to protonate. We end up with what we call a proton transfer reaction, where one of these protons ends up on that oxygen. All right. So now we have this carbon bonded to the nitrogen and amine, this OH up here. We have some mild acid around. This oxygen will get protonated. We'll attack this hydrogen of our mild acid, protonated, to make this ugly beast here. Carbon single bond oxygen H2, which is positively charged. Note that's a good leaving group. The lone pair on the nitrogen will form the double bond between the nitrogen and the carbon, and that leaving group will leave. And that gives us this weird beast here where we've got our 2 R groups on the carbonyl carbon still. It's no longer carbonyl. It's double bonded to this nitrogen, which has an H and the other R group on it. Note that nitrogen has 1, 2, 3, 4 groups bonded to it. It is positively charged, but it also has a hydrogen on it. The reason that this actually occurs is because we have some resonance, and we know resonance will make the product more stable than you think it would be. But water will come in, deprotonate that positively charged nitrogen that has that hydrogen on it, and we end up with our imine. Okay. Now, this is only going to work to make these imines if you have a primary amine. You have a nitrogen with 2 hydrogens on it and 1 R group on it, because you need to lose those 2 hydrogens on that primary amine as water to drive this reaction forward. But what if you have a secondary amine? Well, if you have secondary amines, you're not going to form an imine, you're going to form an enamine. Take a ketone here, a aldehyde or a ketone. Here's a ketone, and if we have a secondary amine, nitrogen is bonded to 2 R groups and only 1 hydrogen under mild acid, we will get the carbonyl carbon is going to be singly bonded to the nitrogen. It'll still have the 2 R groups on there, but we'll have a double bond between the carbonyl, what was once the carbonyl carbon, and a carbon alpha. to the carbonyl carbon, and water will be given off. Note, water is a stable molecule, so often we see if one of the products of your reaction is water, that is something that tends to drive the reaction forward because you're making a very stable molecule. One would expect the energy of the products to be lowered because we have such a stable water molecule being made. Plus, we have tricks to get rid of these water molecules, so we can use Le Chatelier to drive the reaction forward if we can get rid of water as it is made. All right, so the mechanism of making these Enamines from secondary amines follows the first mechanism to make Immines pretty closely. The nitrogen of the secondary amine attacks the carbonyl carbon, double bond breaks, putting a negative charge on the oxygen. Note, this nitrogen has positive charge on it, so we get proton transfer. Proton transfer, this hydrogen ends up on that oxygen to make a normal deprotonated amine here. The two R's and the nitrogen in a lone pair and an OH. This is a carbonylamine, and carbonylamines are unstable. The OH will attack the hydrogen of our mild acid and protonate that oxygen, which makes it a good leaving group. Lone pair again forms a double bond between the nitrogen and the carbon, and that leaves. And one would say, wait a minute, I think we're on our way to an imine, nitrogen double bond carbon. Kind of, but now this nitrogen double bond carbon here is positively charged, but there's no hydrogen on there. There's not a hydrogen on this nitrogen that we can deprotonate. So we have a positive nitrogen with no way to deprotonate it to make it neutral again. So what will happen is water will come in and snag one of these beta carbon hydrogens. This carbon was the carbonyl carbon. This is the beta carbon. It has a hydrogen on there. Water will snag that hydrogen. The carbon-hydrogen bonding pair, sigma bonding pair, becomes a pi bond between this carbon and the carbon formerly known as carbonyl carbon. And now we end up with our product where we've got our amine with its lone pair of electrons. It is neutral. It's got both R groups on it. And we have a carbon-carbon double bond from the carbonyl, from the alpha carbon to the beta carbon here. Okay. Note, in both those reactions, we had a ketone or aldehyde. We added a primary or secondary amine under mild aqueous acid, under mild acid conditions. And our product was the Immine or the Enamine plus water. We can reverse this reaction. We can do hydrolysis using water to break it apart. If you see you have an imine, a carbon double bond nitrogen, if you add mild acid, you can break it up, and it's just the reverse reaction. And so we say, okay, if I have an imine and I add water, break it up, what does this become? Well, this had two R groups on it. This becomes a carbonyl here. That's the ketone. And this adds two H's to it, and that becomes a primary amine. So if we have an imine, we will add water to make a carbonyl and two H's to make the primary amine. We see if we have an enamine, okay, here's a carbon bonded to a nitrogen, looks like a normal amine. Oh, but here's a carbon-carbon double bond. The carbon containing the nitrogen is also part of a double bond. That's an enamine. We know if we add water to it, the enamine, the carbon part of the enamine becomes carbon double bond oxygen. We add the oxygen to there, and we add hydrogen here and a hydrogen to make this secondary amine.